Hello, everyone. This is a presentation on the latest project that we did using Vissim in British Columbia. And for those of you who don't know, there's a country north of America. It's called Canada. Uh, uh, so, so for our project, this is Highway 1. This is basically running across the whole country, and we are in Vancouver, BC area, so on the west side. And as you see, this stretch of the Highway 1 is just east of Vancouver, greater area, and is feeding into Vancouver. There is very heavy traffic on this 4-lane divided highway at this section. So diving in, why is this project happening? Like a lot of projects, there are issues with congestion as well as safety. Looking at the numbers for this corridor, there is an 80,000 ADT for this 4-lane corridor. It's been growing very fast, and it's expected to be growing an increase of 33% by 2035. There is a heavy presence of trucks and heavy vehicles in the corridor, 16% on average. We have sections that are having more than 20% heavy vehicles. And on the safety side, the collision rates are very high here, 4 times the average, provincial average. And 40% of these collisions are resulting in injuries. So there is high expectations for what these projects, series of projects for the widening of Highway 1 are going to be bringing. So the focus of our presentation today is going to be this one interchange, 264 Street interchange. And there has been a Vissim model developed during the concept planning for this project. That model was evaluating the congestion on the highway, and basically was anticipating a very long queue at the interchange for the eastbound, which is about 4 miles long. So that was the reason why this project was started. And for the stretch of the road that I showed you in the previous slides, we received a Vissim model that encompassed our study area and basically was further divided to 3 sections with 1 consultant for each doing the Vissim job. And the model was shared between the consultants. We were focused on the area highlighted green here. The length of the model that we got was like about 40 kilometers with all the interchanges that you see, but we were only interested in the green highlighted area. And we had a tough decision to make at the beginning of the project. So we received the model and we started running the model. It was very slow because of all the static routes that was built into the model, and that had a reason because the model was set up as a DTA, and then there was later was transformed into static routes. So we had lots of static routes that had 0 numbers in them. So they weren't doing anything, but they were just in the model and they were slowing down the simulation runs. We cleaned up those, but we had another decision to make, and that was regarding the unserved demand, which we're seeing at the end of the runs. So it was not happening at our area, study area, but it was rather happening east. And because that unserved demand was existing there, we were not receiving the full demand that was expected to be received in our area. So the decision here was whether we had to run with this model, take it the way it was, and just live with that unserved demand, or we alternatively decided that we want to cut the model and only work on the stretch that included our study area. that had some challenges with it, in a way that, so when cutting the model at that point, just going back to the previous slide, we decided to cut the model here. The problem was, okay, so we were replacing the demand that was coming from east or going to east at this cut area. But then there was the issue with the fact that in this model and in real life situation, the demand that you have on the east side has to travel from wherever it's being seeded into the network to get to the cut point. So we kind of had to consider this latency of the demand reaching to the cut point. So what we did was we basically we took the big model, we started to gradually improve at bottlenecks, and we had like a rule: we are not adding core lanes, we just work on the timing plans, we work on storage bays and stuff, try to get all the demand flushed through the network, and until the point that there was no unserved demand at the end of the cooldown period. So that's how we replicated that demand at the cut area, and it was well received by the client, and we're glad we did it, because the ones that didn't, they had more issues. So that was how we prepared the model for our purposes. This was the biggest challenge upfront. It took some time for us, but further down the road, it was very easy to work with the model. We had very faster simulation runs, and we were not dealing with unserved demand, which was the question of the client, like, where is this demand going? But it was not happening in our segment. So what we eventually submitted to the client was the same model cut as said, and we also added, expanded the network around the interchange, because we thought, first of all, we needed to look at some of these newly added intersections like this one here. But at the same time, we wanted to have some metering to our interchange intersections. So we added this intersection to the south, and we had to do some supplementary traffic counts, as well as looking at the land uses. That's what we did, and this is how the model looked like at the end. This brings me to the next part of this presentation, which is basically what challenges we had, and not necessarily all of them challenges, but rather some of them what we did new, something that we hadn't done before. So we looked at the highway itself, we looked at the ramps, the intersections of the interchange, and the additional intersections, and we also had a transit component with this. So for areas that I'm going to touch on in the next slides, the first one is climbing lanes. So there were 3 climbing lanes envisioned for this at the concept planning level. We looked at the ramp, merge, and diverge operations, among others. For the south intersection that you see here, the concept, there was an alternative plan, a scenario that we built later that would replace this signalized intersection with a dual lane roundabout. And as you see on the northeast corner of the interchange, we had a transit hub, transit center. We call it a mobility hub there. And we looked at the operations of the buses exiting this, which we will get to in the next slides. So for the climbing lane, as I said, at the concept planning level, 3 climbing lanes were envisioned, and the client asked us to reevaluate the requirements for those ramps, for those climbing lanes. And what we did was we basically created heat maps, but looking at the differential speeds between the general purpose traffic and the trucks. So we set a limit there and said, as soon as the differential speed grows over 30 kilometers per hour, meaning that the trucks are going 30 kilometers or more less than the general purpose traffic, is where we think that a climbing lane is required. We communicated this with the client, They were happy with this criteria. And basically, this is how we reevaluated, and we came up with a conclusion that the climbing lane, as in the concept plan, are still required. The other part that we looked at was the merge and diverge locations. We had not used speeds at these locations before. Our evaluations most of the time for merge sections only consisted of looking at the densities. But since we had the speeds available, we added a second criteria here. So basically, our criteria for the merge sections was a level of service E or better, and an average speed of 70 km per hour or higher. The standard merge as designed by our design team were all 200 meters. So we started from there and we increased the length till we got to a satisfactory point, which was meeting both criteria. For the eastbound on-ramp, we came up with 250 meters, and the westbound was 450. We couldn't get it to work with shorter speeds. We know that we were kind of like leaving the realms of merge and going into parallel lanes. So this is where, like, when we were looking at HCS, it was out like off the charts of the HCS, but in general, HCS results were confirming what we were seeing with VISIM. So with this one, for the westbound on-ramp, it was designed as a dual ramp at conceptual level. We reduced it to one lane, and basically with increasing the parallel lane for merge, we kind of managed to get the desired operations there. As for the roundabout, this was probably one of our biggest challenges, and this has not been the first time, but this one was a dual lane roundabout for the south intersection, as I mentioned earlier, and we saw big discrepancies, very big gaps between what CEDRA was suggesting, what VISIM was suggesting initially, and additionally, we had to look at FHWA and their graphs. So basically what we saw was running this in CEDRA was showing a gridlock. Nothing was working. Everything was level service F. We went to FHWA. It was showing that the capacity is still there. So it should be like FHWA was showing this very rosy, while the other one was very dark. So we had to do some fine tuning and manual calibration of the roundabout, and kudos to VISIM because we took your example, the dual lane. We started from that. We just forget about the CEDRA and FHWA and started from scratch. We started working with a combination of conflict areas as well as priority rules, and we said basically everything. We readjusted everything in them. We had to even add dummy links, as you see here. No, not here. I'll tell you where. Here. Sorry, I'm not showing it right there. Anyhow, so with a combination of those, the results were sitting somewhere in between what CEDRA was suggesting and what FHWA was suggesting, and this was also approved. We think that VISIM examples are very good starting points for a lot of projects. The one last point that I want to touch on is about the transit mobility hub and transit priority rules. So this needs a little bit of explanation here. Basically, this is the car parking area. This is the transit area that you see here. So we have transit on the highway, both eastbound and westbound direction, and those guys can access the transit mobility hub via the bridge and into the transit, but then they all exit at this point here. So what's happening here is that we have the north intersection, which is pretty congested. We have a very high northbound right turn flow. It's a free flow, but it's about 1,300 vehicles an hour. And basically the buses had to cross this street and they wouldn't find proper gaps to do their maneuver, as well as sometimes they would get trapped here at this intersection and additional delays would be added to them. What we started to do basically was to think of the ultimate solution, which is preemption. So what happens if we do preemption at this intersection? It would, as expected, it would just make things worse. But it gave us a point of like how bad things could get if you want to give the highest possible priority to transit. And then we looked at early and extended greens as a medium impact solution to this. And that's when we went back to the client and said, we think that an early extended green of this much, 20 seconds, would be a solution. And they said, how does this work? And said, yeah, you have your transponders on your buses. And they talked to the controller and they said, no, wait, no transponders, no nothing. We only have buses. So this is when we went back and we started thinking about this again. And the solution that we found was not at all complicated or even a TSP in its own. All we did eventually was we just introduced. So basically, let me tell you about this. So basically, what we did was we gave these guys a signal that would cut the northbound traffic, let them through, and then consequently give them a northbound left. So you can see that here. And basically all that was these two, and basically all that was required in order to get the transit into an acceptable level of service and have the minimum impact on the general purpose traffic for us was just introducing or serving this for a second time in the timing plan. So this was a simple trick. Maybe we could have thought about this at the beginning, but our minds were set of like TSP, okay, it's either preemption or early extended green. So maybe the point that I just want to make at the end of this presentation is that maybe the solutions are simpler than what we think at the beginning. And yeah, we introduced that second serving of the transit, and that basically brought everything down to level of service D with minimum impact on the general purpose traffic. This was in no means any scientific. It was just our hands-on experience with Visim and how we use it day to day. And yeah, that's about it. That's all I had for this. My name is Amir Alizadeh, as Brandon introduced me. I had Berkeley Law working together, but he's here if you have any questions. And yeah, that's it. Thank you very much. Thanks, Visim, for the opportunity.